Okay, welcome to the black hole. Uh, I must start off my talk by saying a few words of appreciation for the team, and especially for Nayyar Afaq, and he's not actually here, for giving us this. What's happening? Okay. So for giving us this time slot so that we can present here. Okay, so let me introduce myself. My name is Ahsan Hayat, and I have completed my master's in physics, and I am currently associated with National Center for Physics, where I'm somehow trying to learn the experimental particle physics and the data analysis. Okay, now the question is, how am I related to the guest today? You may know that last year a Pakistani team was selected in a competition called Beamline for School. I was actually one of the supervisors. The other supervisor, he might be here in a while, and then you can catch him up later and ask the questions if you, for example, want to have few tips. If you are interested in the next year's competition, or if you want to somehow, if you have any goals for CERN in your life. So I guess he can share his experience very well. And of course, you can ask me questions as well, because I was also the part of that team. So we were invited by the CERN, and then we went there for 2 weeks. And yeah, so Markus Joos, our worthy guest, is actually the coordinator of this program. And amongst his duties is actually the education outreach, and probably this is the reason why we are here today. So yeah, so this was, I will not be actually talking much about Markus, because this is in the theme, so he will be introducing himself. Well, let me tell you a little bit about him, that he is actually a German guy with a very beautiful German accent, right? You will be hearing him right now. And he is a software developer at CERN, and he has served almost for like many years. I actually do not remember the exact figure, but of course he has served for so many years there. And nowadays his primary job is for the education outreach and like looking such projects. So and of course he is a very interesting guy. He accompanied us for almost like 2 weeks, and he provided us the best comfort of our life that we cannot forget. Mansoor is here. He was actually the part of that team, so you can also ask him. That Markus is, of course, a very interesting person. For example, his interests range from, like, apart from science, of course, this is one of his main jobs. But he is, of course, interested in music, art. For example, when we visited his house was just next to the Jura Mountains, the famous French mountains there. So yeah, and he has a complete room dedicated to music. And since we met, we actually kept on sharing our ideas. Like I introduced him to my interests, like what I know about the Eastern philosophy, and of course he shared his interest in music. Furthermore, he loves to know about the culture. So I introduced my culture as well, and he keeps on introducing his culture as well to me. So I guess this is a little bit of introduction, and in detail you will be hearing from him. So I guess this is enough for right now, and I guess I should hand over the mic to Markus. Okay, so can you please?
Okay.
Okay.
Well, Ahsan, thank you very much for this very kind introduction. And well, I'm happy to meet you this afternoon.
Yep.
To talk a little bit about science, a bit about engineering, a little bit about inspiring teenagers to become the scientists or the engineers of the next generation. I hope you can see the slides that I'm sharing. And
yes, we can share. We can see the screen.
Okay, perfect.
Yep.
Good. Then let me go ahead. So, what is the plan for the next 90 minutes? I'm starting by giving you an introduction to the science that we are doing at CERN. This will take about 40 minutes. Then I have prepared some slides for the Beamline for Schools competition. Well, that's about 15 to 20 minutes. And then, well, I'm just going to take as much time as it needs to answer your questions. So let's start with part one, with CERN, and well, about myself. My name is Markus Joos. Well, from my time as a teenager, I've always been interested in computers. Well, here you see the first computer that I had, my first printer, and a Mandelbrot Fractal, which was the result of one of the first computer programs that I have developed as a teenager. I then went to study technical engineering in Germany. By 1993, I was employed by CERN. Initially, I did a lot of software development. I am still a member of the Atlas experiment. I am still developing software, but not as much as I did in the past, because I now have other duties in project management, in education and outreach, well, as Ahsan has already mentioned. Well, here you can just see well, a few lines of code of a computer program that I've written and a picture of the computer that this program is running at. It is a part of the readout system of the Atlas experiment. This means that some of the data that led to the discovery of the Higgs particle in 2012 has been moved through this computer system by software that I had developed. So CERN, let me start by explaining what the acronym CERN means. It is of French origin, Conseil Européen pour la Recherche Nucléaire. This is the title, under which back in 1952 politicians and scientists have met in Paris. Their aim was to re-establish a research infrastructure in Europe. Well, remember that this was only 7 years after the end of World War II. And then after 2 years of negotiations in 1954, the European Organization for Nuclear Research was born. But by that time, the acronym CERN was already sticking and has not been changed anymore. Over the years, CERN has grown. We now have 23 member states. We have a number of associate states. Pakistan is one of them, which means that both engineers and scientists from Pakistan can participate in the research projects at CERN. The organization itself has a staff of about 2,500. There is also a lot of students at CERN, close to 1,000. And of course, there are more than 11,000 users. These are scientists not paid by CERN, employed by their respective universities. And of course, scientists from Pakistan are involved in many of the experiments that are being conducted at CERN. The main mission of CERN is to do fundamental research, of course. We are operating accelerators in order to enable experiments in particle physics. But we are also putting an emphasis on education. Well, that's what we are doing this afternoon. We put a second emphasis on technology transfer. Going to give you some examples of that towards the end of the first part. And we also will try to promote international collaboration. But let's start with fundamental research. Well, mankind has always asked itself, what is matter? Some 2,500 years ago, Greek natural philosophers had the idea that matter could be composed of atoms, but they did not have any scientific devices that would allow them to do any experiments to, well, understand really what matter is about. This only became possible at the end of the 19th, beginning of the 20th century, when in experiments like the ones done by Rutherford and Geiger, it became clear that, well, atoms not only exist, but that they have an inner structure. Today, we know that an atom is made up of a cloud of electrons, and inside of them one would find a nucleus. A little bit later, beginning of the 20th century, other scientists started to investigate the structure of atomic nuclei, and they identified particles inside that we now know as protons and neutrons. And finally, in the 1960s, a structure was found inside of protons and neutrons. Today, we know that in each of these particles, one would find 3 quarks. These quarks, as well as the electrons, are, to the best of our knowledge, truly fundamental particles, which means that there is nothing inside of them. You cannot break them up to see what they are made of. They are really elementary. Now, let's look a little bit at how science works, and in particular, what roles observation, theory, and experiment play in science. I have made up here, a little bit of a simple example. We take an object and we throw it down from a tower. The observation that we make is the longer the object is falling, the bigger is the distance that it travels. So we can come up with version 1 of a theory. The distance that the object falls is proportional to the time. S equals c times t. Fine, we have a theory. Now let's make an experiment. Here is the data that we get. We measure that after 1 unit of time, our object has fallen 1 unit of distance. After 2 units of time, the object has fallen 4 units of distance, and so on. If we then compare this data with our theory, we see that it doesn't fit. So our theory must be wrong. Therefore, we go back to the data, we look at the data more closely, and we try to find a formula, an equation that matches the data. So here is the second version of our mathematical model, S equals c times t squared. And if we now compare this, we see it matches the data, and we have sort of understood how objects are falling. Well, of course, you understand, this is more or less the experiment that Galileo has done in Italy about 400 years ago. Let me now give you a more recent example that shows how powerful this method of using observations to build theories and to bring them in agreement with experiment can be. Here we have an atomic nuclei. This nuclei, as we have already learned, is made of protons and neutrons. And we know from Albert Einstein that mass is a form of energy. This means that the mass of these protons and neutrons can be seen as an energy. It is the mass of the nucleus multiplied by the square of the speed of light. So this atomic nucleus has a mass E1. What happens now is that one of the neutrons inside of this nucleus decays into a proton. In order to conserve electric charge, a negative particle has to be produced, an electron. And we now have 2 bodies. We have the atomic nuclei with a decayed neutron, and we have an electron. These 2 bodies both have a mass and therefore an energy, E2, E3, and they also have a kinetic energy because they are moving in opposite direction. So we have now 4 different energies, and we can make a sum. If we make that sum, we see that the sum of these 4 energies is smaller than the energy that we had attributed to the nucleus before the decay. Now, that is something that no physicist would like to see, because it looks as if the conservation of energy is violated in this beta decay. And in fact, in 1930, there was a scientist called Wolfgang Pauli who did not want to believe that beta decay violates the conservation of energy. Therefore, he postulated that there must be a particle in this decay that nobody had ever seen. He called it the neutrino. But this was pure speculation. It took until 1956 until other scientists managed to detect neutrinos in quite complicated experiments. But then it became evident that both the mass and the kinetic energy of this neutrino is exactly what's needed to balance the energy equation here. So by making observation, by using some theories, by doing experiments, it was possible to postulate a particle that was discovered 26 years later. Good. Well, let's go back a little bit more to practical aspects. We are going to see soon that in order to do particle physics, we need accelerators. But how do accelerators work? On the picture here, you have the first particle accelerator built by Ernest Lawrence in 1930. You see it fits into a palm and it's not very complex. There are two half circles. Between these half circles is an electric field, an alternating electric field. Each time a particle, a proton in this case, crosses the gap between these two half circles, it will be accelerated by that electric field. In addition, we need a magnetic field to curve the trajectory of this proton to keep it inside of this box. So the proton starts in the center and then it spirals, becomes faster and faster, and eventually it will exit from this small accelerator and it can then be used for experiments. Over the years, CERN has built a large complex of accelerators. We have about 10 machines of different size at the moment. We can accelerate different particles, not only protons, also antiprotons, ions, neutrons, isotopes, in order to do a diverse range of particle physics experiments. These accelerators, they fall into two main categories, linear and circular accelerators. At the very start of our particle racetrack, we have a linear accelerator. We take a bottle of hydrogen gas. We ionize the hydrogen gas. This happens in this small chamber that you can see on the left side of the image. And then we inject the proton beam that we get from this ionization chamber into a linear accelerator. It is 76 meters long. And between the two ends, we have an electric potential of 160 million volts. Therefore, the protons are accelerated to an energy of 160 MeV, which means that once they have reached the far end of this linear accelerator, they are moving roughly at 40% of the speed of light. We then transfer these protons into circular accelerators. Here is a picture of the smallest circulator that we have at CERN. It's actually not an accelerator, it's a decelerator for antimatter. But I've chosen this picture because it gives you a nice overview of the elements that you find in such a machine. For example, the bending magnets that keep the particles on their trajectories. Here is a few pictures of the proton synchrotron, another accelerator at CERN, but I'm going to come back to that in the second part of my presentation when I talk about Beamline for schools. Here is an aerial image of the CERN site. On the right-hand side, you see Lake Geneva and the airport. On the left-hand side, you have the Jura Mountains. And the big circle that you see, of course, not visible when you come to Geneva because it's 50 to 100 meters underground, is the big 27-kilometer LHC accelerator. Inside of this accelerator, we have beams of protons at very high energies. At CERN, we are able to accelerate protons to an energy of 6.8 tera-electron volts. This means that these protons were accelerated by an electric potential of 6.8 million volts. That makes the LHC the most powerful accelerator worldwide. But nevertheless, I always find it interesting to translate these units into something that refers more to our domain of experience. 6.8 tera-electron volt, that's the kinetic energy of a mosquito flying at 0.5 kilometer per hour. So by human scales, not a big energy, but if you concentrate that energy into one proton, you can do very, very interesting science. We are, of course, not accelerating single protons. We make clouds of protons. Such a cloud would contain 100 billion protons. And we can even fill the LHC with many of these clouds, such that we can produce billions of particle collisions every second. Well, in order to realize such an accelerator, a lot of high tech is needed. One example is superconducting magnets. In order to keep these protons on their circular trajectory, so to compensate the centripetal force, we need the strongest magnets that can be built. Magnets that are built from ordinary metals like copper and operated at room temperature, they are limited in their strength to about 2 Tesla. But for the LHC, we need a magnetic field of more than 8 Tesla. And that made it necessary to use superconducting cables. Metallic alloys, niobium, titanium in our case, that once they are cooled to very low temperatures, 1.9 Kelvin in our case, lose their electric resistance. So the whole LHC is a very heavy assembly of magnets, cooled down to almost absolute zero in order to be able to realize very, very strong magnetic fields. And you may therefore get a bit of an idea why most of the people that are employed by CERN are actually not physicists, but engineers. Engineers that not only develop these magnets, they develop all the electronics that's needed to control such a system, and of course also the software that is running on these electronic systems. The purpose of the accelerators is to enable experiments. These experiments are, strictly spoken, not CERN experiments. CERN is providing the infrastructure to international collaborations. These collaborations propose experiments. They will also finance, build, and operate them. All of these experiments are centered on fundamental research. We are trying to understand the most fundamental levels of the universe. We are asking questions like, what are the smallest constituents of matter? What forces do exist? Why do particles have mass? This is science in the service of society, which means that all of the results that we have at CERN are public. Also, all of the technology that we are developing is public. We are not doing any research of military nature. We have no secrets. That, I think, is something that is very essential for fundamental science. So here is what happens inside of a particle detector. In this animation here, you see the collision of 2 atomic nuclei. So in white and in red, you have the protons and neutrons of these 2 nuclei that are colliding. And in this collision, some of the kinetic energy becomes free and it produces secondary particles like the blue and the green ones. And these secondary particles are the one that we are interested in. But how can you see particles? Well, there is a very, very simple way of making particles that are not visible to our human senses, visible to us nevertheless. The picture that you see here is that of a cloud chamber that I have built myself. There is some foam to insulate it. There is a block of cold metal. There is a tank for hot water. And inside of these plexiglass screens is a sponge that is soaked with alcohol. What happens when you put this into a dark room and illuminate the inside with a flashlight is that you can see traces of particles that cross this alcoholic vapor. They make some of the alcoholic vapor condensate. So what you see here, these tracks that I've taken in my cloud chamber, are not the particles themselves, but the droplets of the alcohol that are formed along the trajectory of the particle. A very similar technique has been used for many, many years by scientists, not only at CERN. It's called a bubble chamber. The difference between the bubble chamber and the cloud chamber is that in the bubble chamber you don't have a gas, but you have a liquid. Apart from that, same idea. You make some kinds of droplets that you can photograph. Here on the left-hand side, you have a picture of such a bubble chamber image. Experiments that have used these techniques in the 1920s, 30s, 40s, 50s, 60s, 70s have eventually led to what we call the standard model of particle physics, which is a collection of knowledge, in particular mathematical equations, that tell us how the universe works at the lowest scale of size. 12 particles have been identified, 6 quarks and 6 leptons. In the group of the quarks, we have 2 particles that are stable, the up quark and the down quark. If you take 2 of these up quarks and 1 down quark, you get a proton. Take 2 down quarks and 1 up quark, you have a neutron. And by adding the electron from the lepton family, you can make all the chemical elements that we know of. So all the material world is made of mixes of only 3 particles, up quark, down quark, and electron. Most of the other particles that we see on this slide are not stable. For example, the muon, the heavy brother of the electron, has a lifetime of 2 microseconds. Muons can be produced. Nature is also producing muons all the time. But after 2 microseconds, they disappear. They decay into electrons and neutrinos. Well, the second main message here is that in nature there are 4 fundamental forces. Probably the force that we know the best is the electromagnetic force. It is tying electrons to atomic nuclei. It allows atoms to make molecules. And of course, electromagnetic waves are also what make light, X-ray, radio waves, etc. The weak force is constrained to atomic nuclei, to the particle level, and it allows particles to change their nature. For example, when a muon is decaying into 1 electron and 2 neutrinos, that is the weak force that makes that possible. The third one of the fundamental forces is called the strong force, and its job is to keep the quarks glued together inside of the atomic nuclei. These 3 forces here with the green background are those that are described by the standard model. You can also call them the forces of the quantum physics. There is one more, gravity, which actually is not a force but an interaction, and this is described by general relativity. So far, even though physicists are dreaming of that for many, many decades, it has not been managed to unite these four forces in one mathematical model. That's the big goal of theoretical physics, to find one set of mathematical equations that would describe all four forces. Now, on the way to completing the standard model, CERN has made one very important step. Back in 2012, we have found the Higgs particle, a particle that was already theoretically predicted in 1964, among other by the two gentlemen that you can see here on this image, François Englert from Belgium and Peter Higgs from Scotland. They asked themselves why things are heavy. Why do objects have a mass? In the 1960s, this was not yet understood. So they proposed that there is a field, which later was called the Higgs field. Particles like electrons, protons, would interact with the Higgs field, and by that interaction, they get a mass. So you see, we are again back at our game of observing, making theories, and doing experiments. In that particular case, the experiment came 50 years after the theory, and thanks to the results of these experiments, François Englert and Peter Higgs got their Nobel Prize in 2013. In order to find such exotic particles, we have to build very, very complex experiments. Here are the four detectors at the LHC, Atlas, CMS, ALICE, and LHCb. I'm going to show you a few details of the Atlas experiment, because that's the experiment I am working for myself. The Atlas detector is the biggest experiment that we have at CERN, 46 meters long, 25 meters in diameter, total mass of 7,000 tons. And it is a very, very big international collaboration with more than 3,500 members from 35 nations. Well, if you want to know more about the Atlas experiment, I invite you to join me on the 26th of January. I'm going to go down to the Atlas experiment with my video camera. This is one of the events that we are organizing for participants of the Beamline for Schools competition. Inside of these detectors, protons are accelerating are colliding at very high energy. And every now and then, such a proton-proton collision results in the production of a Higgs particle. Well, producing a Higgs particle in a proton-proton collision is not very likely to happen. I'm illustrating this here with these 41 coins. Imagine you take these 41 coins into your hand, you throw them up in the air. The probability for finding a Higgs is the same as the probability for all 41 coins landing on the floor such that the same side is facing up. Therefore, we have to collide many, many protons in order to produce a reasonable number of Higgs particles. So these were some examples for LHC experiments, but CERN is much more diverse than that. Here you see some examples of LHC independent research. We have, for example, a world-leading facility for research on antimatter, but we are also doing research that is a bit more applied. One example here is to find a more optimal geometry for doing PET scanners. PET, positron emission tomography, is a method that's used in medical diagnostic, in particular to find cancer in humans. And there are people at CERN trying to improve these PET scanners in order to, have more modern, more powerful diagnostic technologies. So a lot of success since the foundation of CERN back in 1954, but we are far from understanding everything. And here is one example for a question that nobody has yet been able to answer. What is dark matter? Well, if you take a telescope and you look at galaxies, you see that these galaxies are rotating. And as soon as something is rotating, there has to be a very basic equilibrium of two forces. The gravity that is pulling these stars towards the center of the galaxy has to be compensated by a centrifugal force that is, of course, due to the velocity of the star itself. If you look a little bit closer at the conditions inside of this galaxy, of any galaxy, you will see that the centrifugal force is much bigger than the gravitational force if we just take the visible matter into account. In order to have these galaxies stable, and we know from observation that they are stable, there has to be extra gravity, actually 5 times more than the gravity of the visible matter. But so far, nobody knows what the source of this extra gravity would be. We have given it a name, dark matter, but we don't know yet what dark matter is. And that, motivates us to keep doing research, to build maybe in 10, 20 years from now, the next generation of particle accelerators and experiments to hopefully one day figure out what dark matter is about. But let me now show you some examples of technological transfer. And let me be clear, what is motivating us at CERN is not the technical spin-offs. What motivates us is our curiosity. We want to find out what laws govern the universe at the most fundamental level. But we have seen that whenever you learn something fundamental, you can use that knowledge, sometimes not immediately, sometimes it takes many, many years, to innovate new technologies. And here is an example for such an innovation. It's the use of accelerators in medicine. On the left-hand side, you see an X-ray image of a human head. The patient here has a tumor cancer that is located inside of the brain. Brain tumors are often treated with radiotherapy. The idea of radiotherapy is that by directing some ionizing radiation onto the tumor, one would destroy the DNA, the genes of the tumor cell, and therefore make it impossible for these tumor cells to replicate. For many, many years, and it is actually still happening today, the radiation of choice is X-ray. Well, not because X-ray is working very well, but because it is relatively cheap to make. But you see on this color-graded dose distribution profile that a lot of the X-ray energy is absorbed by the healthy brain in front of the tumor. And there is also some absorption by the healthy part of the brain that's located behind the tumor. This means that in order to kill the tumor, one has to tolerate some damage to the healthy part of the brain, which is of course not in the interest of the patient. About 100 years ago, there was a British scientist, William Bragg, who asked himself out of curiosity how heavy particles like protons behave when they are moving through matter. And he found an effect that now in literature is named after him. It's called the Bragg peak. So a proton that would move through a human body will first deposit relatively little energy. Then it reaches a crucial velocity, it deposits a lot of energy, and it stops. From this second dose distribution profile, you can see that the amount of energy absorbed by the tumor is the same as for X-ray. But the effect, the damage on the healthy part of the brain is much, much reduced. Well, what's the downside of this form of therapy? You need to operate a complete particle accelerator. Not as big as the LHC, but still a machine with a circumference of 50 to 100 meters and with a cost of about 150 million US dollar. But there are more and more of these centers being built worldwide, and until today, more than 400,000 patients have been treated in this way. Two more examples of applications of our technology in other domains. Here you have an image of a particle detector that has been developed at CERN. It is called TimePix. We have developed this image sensor in order to detect elementary particles. But the scope of applications of this sensor is much wider. You have here two X-ray images of a human hand. And you see something that you probably have not yet seen in X-rays. These images have a color. That's because this chip is very sensitive and it can discriminate different X-ray energies. So that makes it possible with a little bit of computer technology to give the different parts of the body, like the bones, the muscle tissue, the blood vessels, different colors. And that, of course, makes it much easier for a physician to understand what is happening inside of the human body. Here is, on the right-hand side of the picture, yet another example that I myself find quite cool. One is using natural muons, muons that are produced by cosmic radiation impacting on the atmosphere. And you take a muon detector and you carry it around a volcano. This is a volcano in Italy, close to the village of Naples. These muons, they are so energetic and their interaction with matter is so low that they can fly through the entire volcano and they can be detected. Then with a little bit of, mathematics and computer science, one can use these muons to make something like an X-ray of the volcano. So what you see here, this sort of a little bit blurry gray shape here, is the magmatic chamber inside of the volcano. And if one is repeating these surveys at certain intervals, one can find out about the dynamics of the volcano and maybe learn about an eruption that's likely to happen. So with this slide, I'm at the end of the first part. I'm now going to part 2 of my presentation, which is on Beamline for Schools. The basic idea of the competition is very simple. We are inviting teams of high school students to propose a particle physics experiment to us. And we believe that this is a very nice opportunity for you to get in touch with, not only the world of physics, but the world of science in general. And then, eventually, the winning teams of the competition are invited either to CERN or to DAISY laboratory in Hamburg in Germany to perform their experiments. Well, I'm not going through all the details of the slides. You can find a lot of that on our website. And of course, you have some people in the room that have won this competition in the past. Let me just point out that it is a team effort. Teams should have a minimum of 5 participants. that should be enrolled in high school in the current school year. And well, in addition to the main prize, which is an invitation to CERN or to DAISY, there are other prizes that one can win. Well, here is very briefly some information about the evolution of the competition. Well, we started in 2014, and you can see that the number of teams that are participating from year to year is increasing. Last year, we had almost 400 participants, and quite a number of them from Pakistan, actually. So here is just a map showing where we are located. Geneva here in the western part of Switzerland, and Hamburg, the German lab for high energy physics, is located close to the border of Denmark and Poland. What you have to do if you want to participate in this competition is to, first of all, have an idea for a particle physics experiment, and then you write down your proposal. Well, there is a limit of the number of words, and you can, in addition, if you want, do a creative video to explain our proposal to us. The proposal, and if you go for the video as well, has to be submitted to CERN by the 10th of April. What is the most important criteria when we are evaluating the proposals is the feasibility. If you have doubts about the feasibility of your experiment, well, try to contact experts. Maybe your teacher, maybe a physics prof at the university, or if you want, you can also drop us an email. You have the mail address here, bl4steam@cern.ch, and we are certainly going to comment about the feasibility of your idea. In addition to that, well, we are looking at the motivation and the creativity of your experiment and your ability to follow the scientific method. There is an extension to the competition. We have a category that we call Outreach Prize. These outreach prizes are completely independent from the Beamline for Schools competition itself. What we want you to do to win one of these outreach prizes is to describe an outreach activity that you have either already done or are promising to do in your local community. These prizes are optical telescopes that are being offered by Jean-Pierre Grothard, who is also connected today. And I know that Jean-Pierre puts an emphasis on inclusive science. So if you want to win one of these telescopes, please propose an activity that emphasizes the inclusivity of science by bringing science to, for example, communities that otherwise would not have such an opportunity. Good. Back to Beamline for Schools. What are the requirements? We are providing a beam to you. This beam is going to interact with some sort of target. This can be a sample of material. It can also be a detector that you are constructing yourself. And there will then be additional detectors provided by us to show what happened in this interaction between the beam and the target. This takes place at the proton synchrotron. You have here a picture of the large experimental hall where the experiments are taking place. So this is where the winners are going to build up their experimental assembly in September. We are providing at CERN a beam of mixed particles. The beam can either be positive or negative. There can be particles like electrons, pions, kaons, protons, well, if you're very lucky, even some antiprotons. And we can realize a range of energy between 0.2 and 15 gigaelectron volts. But you may have to, well, read a little bit of theory, and we have a very nice document on our website in order to understand the details of that. But well, let me assure you this is not very difficult for you to grasp. Here are some pictures of the facility at DESY, and the beam at DESY is a bit different from ours. The energy is relatively similar, also the size of the beam is similar, but at DESY the beam is a pure electron beam. Here is an example of an experiment that we have done a few years ago. You see how different detectors, delay wire chambers and scintillators in this case have been assembled. In the middle there is a black box, and inside of that black box was a so-called Cherenkov detector that was built by a team from Mexico that had won the competition in that year. A few words on the detectors, which are of course our eyes that allow us to observe particles and their properties. We are providing you scintillators. Scintillators can, well, first of all, tell us when a particle went through the experimental area. We can also measure them. We can also use them to measure the time of flight of a particle, which allows us to calculate the particle's speed. We have tracking detectors like delay wire chambers, micromegas, and pixel detectors. The purpose of all of these tracking detectors is to show particle trajectories. Then we have particle detectors like this one here, which are colorimeters. They don't tell us where the particle was, but what the velocity of the particle was. And there is well, yet another type of detector, the multi-gap resistive plate chamber, that is sort of a hybrid between tracking of particles and measuring the velocity. So you should consider these detectors to be Lego blocks, and you would arrange them in a clever way to get the data that you need in order to find the effect that you're looking for. So to make this a bit more practical, let me show you 3 examples of winning proposals from the past. In 2016, we had a winning team from Poland. They tried to understand how back in the 1970s, muon radiography, that I was already introducing to you, was used in order to explore the structure of one of the pyramids in Egypt. At that time, researchers placed a muon detector under the base of the Khafre pyramid, and by measuring the muon flux, they got well, a chart that you can see here on the top right. So you see here how many muons arrived at this detector. It looks at first glance a little bit messy, because one has, of course, to take the geometry of the muon into account. But one can see that there are certain angles where the muon flux is not as high as expected. The expectation, of course, is the black line. And in particular, there is one area at about 270 degrees where the muon flux was much higher than expected, and that would be compatible with the pyramid having a yet undiscovered chamber at this location. So the students from Poland wanted to try this themselves. What we did was to shoot a beam of muons through a block of limestone, and to measure how the limestone would absorb the muons. And then at the very end, once we had understood the absorption properties of the limestone. I made from 9 of these limestone blocks a pyramid. You see the pattern here on the top right hand, on the bottom right hand. And of these 9 blocks, I removed 3 and then I covered it up. And I let the students shoot the muons across in order to figure out what the pattern of limestone blocks was that I had set up. And with the calibration data that they had taken in the first week of their experiment, they were able to reconstruct the shape of this target. So they have discovered, analyzed the structure of their own pyramid. In 2020, we had a winning team from Germany. They realized an experiment that was based on Cherenkov radiation. Cherenkov radiation, without going too much into details, is a kind of radiation that happens when particles are moving through a dense object at a speed that is higher than the speed of light inside of this object. And this kind of Cherenkov radiation can be used in order to diagnose, to measure properties of a particle beam in a very non-intrusive way. So the particle beam passed close to the surface of a block of very clean silicon glass. And because of the charge of the beam, via some kind of effect, Cherenkov radiation was created inside of this silica block, and the Cherenkov light was then detected with a photomultiplier tube. So this shows that one does not necessarily have to do a particle physics experiment. Also experiments that are more on the practical side, on the side of trying out novel detectors, can be equally successful in this competition. And this is my penultimate slide. There is, of course, the success of the Team Particular Perspective from Pakistan that had won the competition last year. Well, they started with the 2 graphs of the beam composition of CERN that I have already presented to you. And it's important to say that these graphs here are not measurements, they are simulations. We have used the computer to simulate what we expect to find in the particle beam. But we have actually never measured it. So the particular perspective team proposed to do a measurement. They came up with a setup of the detectors that would allow them to get data that eventually allows to identify particles and to measure their relative abundance in the beam. And on the right-hand slide of this, on the right-hand side of this slide, you see some images of the experimental setup that was proposed. So I'm closing with the website of our competition, cern.ch/BL4S. Under this website, you can find a lot of information. Well, I hope everything that you need in order to participate. Let me say again, this is not something that you have to do by yourself. There are a lot of people, national contacts in Pakistan, experts at CERN that you can get in touch with to discuss and refine your ideas. Okay, so let me stop the sharing of my screen.
Kindly clap for Markus for such a beautiful talk. Markus, thank you very much. It was such a beautiful talk. It almost encompassed all the aspects of CERN and then Beamline for School as well. And yeah, hopefully it was also understandable for you guys as well, because it was not that intense and of course understandable easily. Okay, so Markus, now this is the time to ask questions from you, but I will start with a question from myself. Well, you see, we know that CERN is actually a laboratory for particle physics, and you have mentioned that CERN actually employs people from other fields as well, right? And probably like in more numbers. So my question is that, for example, there are so many people who have asked me this question, so that I must ask you that, is it like possible for people of other fields like material sciences or let's say laser physics to somehow get an opportunity at CERN? So is it like possible for these guys as well?
Oh, absolutely. Well, let me give you an example for material science. Well, I was showing you an image or an illustration of our particle beam. Inside of the LHC accelerator, we have clouds of protons. These clouds of protons, they have a little bit of a halo, and they can touch the inside of the beam pipe. So if that's the beam pipe, beam is going through the center. Some of the particles of the protons, they scratch along the inside of the beam pipe. And by doing so, they produce electrons. These electrons are knocked out of the metallic surface. And these electrons, they contaminate the proton beam. So the more electrons we have inside of the beam pipe, the less good is the property of the beam. Therefore, we had done a lot of material science in order to find out what kind of metallic alloy would be the best one to line the inside of the beam pipe such that this production of electrons is reduced as much as possible. And there are many other examples of material science. For example, in new superconductors that would allow us to build the next generation of particle detectors and particle accelerators. So, well, material science is something that is very important for enabling science not only at CERN but in many other institutes as well.
Okay. I must mention that not only science is relevant to CERN, there are other departments as well, like HR department. So there's a girl from Pakistan. I exactly cannot recall her name, but actually she is there. And so not necessarily science students, other students can also join CERN. For example, if someone has a degree in IR or some other subject. And well, before opening the session to the audience, I must say a few words about this particular format of the session. You see, CERN actually primarily relies on the knowledge sharing, and that takes place through PowerPoint presentation. For example, if you will visit any department, you will find, like every single day, you will find such PowerPoint presentations happening. So I guess this was the reason why we have chosen this one, so that you must get the experience how CERN actually share the knowledge. Okay. So now you can ask the questions. If anyone has a question, kindly raise your hand so that you can ask the question, Mike. Okay, Marcus, I guess your talk was definitely very of course it covered everything. So I already had so many questions, but now when you completed the talk, it almost covered everything. Yeah, I guess there's a question from my beloved friend Shahriyar.
Hello, Marcus, how are you?
Hello, I'm fine.
Really glad to have you here and amazing presentation. We learned a lot and you all are doing great work at CERN. So I was curious about dark matter because I have done some research in astrophysics and cosmology as well. I recently gave a public talk about dark matter as well. So can you tell us briefly about what CERN has achieved with regards to detecting particle dark matter? Have some strides been made in this direction? What are the latest updates?
Well, CERN has been active in dark matter research in the past, but like all other research institutes around the world, well, we have not yet been successful in making any progress in the understanding of this form of matter. We had, for example, in operation for more than 13 years, an experiment in which we were looking for so-called axion particles. Well, axions and, well, please keep in mind that I'm an engineer, not a physicist, are particles very light with a very weak interaction with matter that have been proposed by certain theoretical physicists as being the particles that dark matter is made of. So we set up an experiment. It was called CAST, Solar Axion, CERN Solar Axion Telescope. And in this experiment, we looked for signals of these axion particles. And in 13 years, we just saw nothing. We retired this experiment about a year ago. But this does not mean that we have given up. There is at this very moment a new axion experiment being constructed in the north of Germany. In order to, well, refine the axion search further, because we are not yet ready to believe that these axions don't exist. The theory that is proposing these axions seems to be very compelling. And you have seen in my presentation a number of examples for well, experimental breakthroughs that came long after the corresponding models were predicted. Well, you've seen that for the neutrino, it took 26 years from the theoretical model to the discovery. For the Higgs particle, it was almost 50 years. So not finding axions for 13 years is no reason to lose motivation. And that's why the search for dark matter is continuing. We don't know if we are going to be successful soon. We don't even know if we are going to be successful at all. But well, we are very motivated to understand this dark matter, which actually does not even have to be a particle. It can also be, well, a different understanding of how gravity works. So by modifying the laws of gravity as they are described by Einstein, one could maybe also find an explanation for dark matter. No, we really have to keep our eyes and ears open. We have to look right and left and well, do more experiments in order to, well, understand how gravity works at large scales.
Okay, great, Marcus. Yes, you are completely correct that we have two different approaches for understanding dark matter. One is to consider it as a particle, and the other is to perhaps change our laws of physics. So those are two approaches. Yes. My second question is related to machine learning and data science. You know that lots and lots of analysis of this certain data uses machine learning algorithms because the amount of data generated is so enormous that we need some like a machine intelligence to parse that kind of data and extract useful information. So can you tell me about like opportunities for students who are interested in machine learning or data science, because we have lots and lots of graduates coming out of Pakistan in these fields who are passionately studying machine learning and data science. So are there any opportunities for those kinds of students related to machine learning or data science at CERN?
Well, machine learning is something that over the last few years has become a very well, important topic in the analysis of experimental data. Let me just give you one figure in order to illustrate the size of the problem that we have to solve at CERN. One of our big experiments, like Atlas, for example, will in operation produce between 50 and 100 terabyte of data per second. So if you would try to store 100 terabyte per second on hard disks, you would fill 10 computer disks with data in every second. So, well, this is an amount of data that cannot be handled. we have to filter the data. We have to identify those data sets that tell us something new about, most cases, Higgs bosons. And most of the data we just throw away. But to build an algorithm, to write a computer program that can handle 50 to 100 terabytes per second is far from trivial. And one of the techniques that we are already today using for this challenge is neuronal networks. Each of the big experiments at CERN has a working group, mainly physicists, that have learned how to build up neuronal networks, how to parameterize, how to train them. And then eventually, data coming from the detectors is given to these networks, and these networks are looking for certain properties of the data. There are, conferences taking place at CERN where we learn about the latest tools in this domain. There are trainings organized for young scientists. This is, of course, also becoming a topic for the schools that CERN is organizing. We have a CERN School of Computing. At CERN, we are not really doing research in neuronal networks. For us, they are a tool. We are using, I'm not a specialist there, but things like TensorFlow, and then we make models and we train these models with our data in order to do the physics that we want to do. And if somebody already has a bit of experience with this technology, well, that's something that will certainly look very good in the CV of that engineer or scientist when he or she is applying for a job at CERN.
Thank you very much. Is there any other question? Yes, please. There are a few questions from.
Hi, Markus. Actually,
Hello, Mansoor.
yeah. We all know that the biggest discovery that CERN has made is the invention of they have made LHC. I have a question that is CERN is planning something big, even bigger than LHC, and if there is, how much time will it take and what contributions it will do in scientific research?
Okay. Well, according to our current plans, we will keep the LHC up and running until 2040. So still 16 years, enough time for all of you to become scientists and to find a position at CERN. At the moment, for the time after 2040, we have 4 different ideas. Well, idea number 1 is relatively conventional. We would just build another circular accelerator, but next time we make it bigger. We don't make it 27 kilometers, we make it 91 kilometers. This project already has a name, Future Circular Collider, and we are already at this moment doing a lot of detailed studies about how to build the tunnel, about the machine that we would put inside. Because this accelerator is bigger and because it would use a new technology of superconducting magnets, it would allow us to increase the energy of the beam by a factor of 10. So it would allow us to open a new window on nature to make observations that could then help us to deepen our understanding of the laws of physics. The second idea that we are following is that of an accelerator that is not ring-shaped but linear. A linear accelerator has the advantage that you don't need these expensive magnets to bend the beam. The disadvantage of the linear accelerator is that its efficiency in colliding particles is not very high. And we have to find a trade-off between these disadvantages and advantages. Well, the last word on that has not yet been spoken. The third idea that we are pursuing is, well, a little bit science fiction. In the last 100 years, well, accelerators have, of course, become more and more powerful, but at the same time they became bigger and bigger. Because the fundamental principles of particle accelerations have not changed a lot. But there is a relatively novel idea, which is called plasma wake field acceleration, that would be a complete game changer. In the accelerator structures that we are using at the moment, they are called microwave cavities, we can realize electric fields with a maximum later you can get it's 23 budget of 1.3. And there has to be a consensus in the society. Can say how the political 30 years. Our society is important.
Okay.
Can I ask one more question?
Of course.
Actually, other than a Beamline for schools, CERN also organizes Solvay Student Camp. Also today is the last date for the Solvay Camps of 2024. But a lot of people will be listening your voice through this platform. So I want you should also guide the students about Solvay Camps. So in the upcoming years, they may not know about it and participate in it.
Mm-hmm. Well, I am myself not at all involved in the Solvay camps. That is something that other colleagues of mine are working at. But if you have any questions, well, you can contact me, and I will then forward your email or your message to my colleagues and make sure that you get all the information that you're looking for.
Thank you. Thank you so much, Markus.
Hello, Markus. My question to you is, how does one prepare or equip themselves with, in order to write a worthy enough proposal for the Beamline for Schools competition? Thank you.
Mm-hmm. What I did not mention yet is that we have on our website one document with example experiments. So experiments that we think are feasible and interesting. And in fact, the team from Pakistan that had won the competition last year has taken one of these examples. And they were not the only team to take this example. A few teams picked it up. But what made us pick this team as a winner was that they have, on the basis of the example, described the experiment in the most complete and the best way. So one approach is to look at the experiments document and to pick the experiment that interests you the most, yes. And then, well, you start learning. What is this experiment about? What's the physics effect behind it? What detectors do you need? And no, you cannot do that by yourself. We, of course, realize that well, at your age, you don't have the background in physics that you need, but you can learn it. And you can get in contact with previous winners of the competition. Well, there is one sitting next to you. You can get in touch with your physics professor, get in touch with people at universities. And I guarantee you, the more you talk to people that are working in this domain, well, the clearer will it become in your mind. And then, well, eventually you will have not only an idea, but you will also be able, together with your teammates, to write it down and to submit it to us.
Hi, Markus. I am Akhtar Tarar, coach of the.
Hello.
I thank you for such a good talk. We spent 2 weeks. That was a very nice experience there at CERN. I want to ask you that please give some clues how we can detect neutron beam.
Okay. Yes, if you look at our example experiments document, you see that there is one idea on spallation. This is an example that I have put into the document recently because I have learned that the colleagues at CERN that are responsible for radio protection have neutron detectors. If you look at the second big document, the beam and detectors document, it will say that all the detectors of Beamline for schools are not sensitive to neutrons. That's because our detectors, like delay wire chambers, like scintillators, all the tracking detectors, they are only sensitive to charged particles. And of course, the neutron does not have an electric charge. What all of our detectors have in common is that they can detect single particles. So when a proton crosses a scintillator, you get a signal and you can record it. The neutron detectors that we have at CERN, and I have to be honest, I have not yet used them myself. These neutron detectors are relatively slow. You cannot get a single neutron signal. They are more like accumulating neutrons over a certain amount of time, about a millisecond or 10 milliseconds if I'm not mistaken. But they are adequate to measuring a muon dose. So the idea of this spallation experiment is that you put a target into the beam, you make the beam interact with the target, and in this interaction, spallation happens. Well, spallation means that neutrons are being kicked out of atomic nuclei, and these neutrons then travel through the target and eventually hit the neutron detector. And in the neutron detector, you can measure the amount of neutrons that are being seen over a certain amount of time. And what can be done then is to, for example, compare different materials for their spallation properties. So not all chemical elements produce the same amount of neutrons. And by putting different samples of materials into the beam, you should be able to measure how many neutrons are being produced. And another thing that could be studied is the angular distribution of these neutrons. So you could put the neutron detector right behind the target and see how many neutrons go into the forward direction. Or you put it at 90 degrees to see how many neutrons are being emitted orthogonally to the particle beam. I have been discussing this idea with our neutron detection specialists. They have told us that it is feasible and that we have the detectors, but we have not yet really worked out all the details with them. So I guess what we need is a team of students that find this an interesting subject and that in, contact with us, work it out to make it, a full experiment.
One of our team, I am registering more than.
Sorry, I can't understand the sound.
I am registering more than one team this year. One of these teams, they are interested in detecting neutrons. So they will try, inshallah.
Very
Okay,
good.
thank you so much, Markus.
Is there any other question, please? Okay, that's it, Marcus. Well, I have a question from myself. The question is about the upgradation of LHC, right? Which is, of course, it's going to happen soon. So can you tell us a little bit about the upgradation of LHC? And apart from this, I would also love to hear from you about the quantum computing initiatives of CERN, because after we left CERN, actually, there was a conference about quantum computing, which I came to know about. And I'm actually much interested in this. So can you please make a few comments on this as well?
Okay. Well, first, the upgrade of the LHC. The LHC was started in 2008, and we are stopping the accelerator every 6 years for 1 to 2 years in order to not only repair small damages, but also to further improve the performance of this accelerator. We had one of these, we call them shutdowns, from 2019 to 2021. In this shutdown, we have changed the pre-accelerators. We have replaced an old linear accelerator by a new one. And we have also done a lot of modifications to the small accelerators that are providing the particles to the LHC. And then in the next long shutdown, which will be 2026-27, we are going to make some small modifications to the LHC, not so much to achieve higher particle momenta. This is not possible, but we are going to massively increase what we call the luminosity. Luminosity is simply the number of particles colliding by unit of time. In 6 years from now, the collision rate will be increased by between a factor of 5 and factor of 10. And that simply means that we get much more data in the same amount of time. This is good for the physicists because they get data quicker. They can do their statistics faster. But it is a massive challenge on the computing side because we have to analyze 10 times more data. Therefore, we are already for years trying to figure out how we can use our financial budget for computing in the most efficient way. And we have talked about it a moment ago. Neural networks are a technology that helps us to do computation in a cost-effective way. Well, the ultimate goal, if you want, is to use quantum computers in order to analyze the data. CERN has started to follow the development of this technology already 6 years ago. Since 2018, there have been 3 quantum computing conferences at CERN. And CERN is also the funding member of a quantum computing or quantum informatic institute that has been founded in Geneva about a year ago. We are in permanent contact with the big companies working in this field, like IBM, like Google, like some companies that are not that well known by name. For what I know, we are more focusing on the sort of software side. We are trying to develop models for how to program future quantum computers. On one side, it is true that in the last 5 to 10 years, quantum informatics has made very, very large progress. There have been a number of technological breakthroughs. But for what I know, the field is not yet at a stage where you could do anything useful with a quantum computer. I'm not a specialist at all in this domain. What I have heard is that in order to do something useful, you need about 100,000 qubits, so 100,000 entangled quantum states inside of such a quantum computer. And the best one that exists at the moment is at 1,000 qubits. There are still 2 orders of magnitude to go. And that's not the only challenge. There are other challenges in what you call the coherence time, the time through which you can maintain this entangled state, which also at the moment is too short in order to do anything useful. Okay. But it's a developing field, and we are not only monitoring the progress, we are also trying, where possible, to make a contribution to this field. And of course, if you have a particular interest in this technology, I can try to find out the names of some colleagues that are working in this domain and bring you in contact with them.
Thank you very much, Markus. Okay. Yeah, there's a question from, please, can you? Here, please.
Good evening, Markus. This is Memuna. I'm not a background of physics, but I'm a mathematician and data analysis. This is a very good session, and it's my first time to know about the CERN. My question is, what about the team of that you made, like the one who knows about the neutron or physics, or every kind of people can be included, like some of maths, some background of material science, or some background of quantum physics? And secondly, what about, is it only winning that competition, or just to join and get some incentives?
Okay. Well, let me start with the second part. You have seen in the statistics that last year we had close to 400 teams participating. Only 3 of them have won an invitation to either CERN or DESY. Well, therefore, if you are participating, mathematically the chance of winning is about 1%. This means that with 99% probability, you're not going to win the competition, but with 100% probability, you're going to learn something. You're going to win in knowledge. And of course, I don't know where exactly your personal interests lie. But at one moment, when you're graduating from high school, you have to make a decision about what you're going to do in your professional life. Are you going to a university? If so, what are you going to study? Or will you go into another professional career? And I think, for teenagers, it's very important to look into different domains. To do internships, to take part in competitions like Beamline for Schools, in order to find out what really you're motivated to do professionally later on. So in Beamline for Schools, we are trying to create an environment for you where you can use your creativity in order to go a little bit outside of your comfort zone and to expose yourself to a field that maybe or maybe not could be of professional interest to you later on. And you will see that, and I'm trying to answer the first half of your question, that science, and I'm not talking about particle physics, I'm talking about science at large, is in almost all domains a team effort, and in almost all domains it is interdisciplinary. Here at CERN we have all kinds of engineers, electronics, we mentioned material sciences, vacuum technology, cryogenics, working together. No one of us can do anything by himself. We always have to bring experts together. And that's also what you see in many other research labs around the globe. So if you find teamwork interesting, if you find it interesting, to really dig deep into a problem until you've understood it, well, then maybe a scientific career is for you. And this competition is an opportunity for you to try this out.
Okay. Thank you very much, Markus. And if my audience allows me a little bit, we have Jean-Pierre with us. So, Jean-Pierre, can you hear me, please?
I can hear you loud and
Okay.
clear.
Jean-Pierre, I guess you must have enjoyed this session, right? And
Yep.
yeah, and the reason I have actually talked about Jean-Pierre is that this is actually the guy behind distributing all the telescopes to the students, right? He has gifted a telescope to the winning team, particular perspective, and currently this telescope is, I guess, at ICB college somewhere, right? And
Yep.
and also this guy is also very much important for the black hole as well, because when I requested him to gift one of his telescopes, he agreed and he gifted a telescope to the black hole as well. So I guess this is the time to give him a round of applause.
Thank you.
Thank you very
you so
much.
much.
Thank you very much for all your efforts, Jean-Pierre. Okay, thank you very much.
You're welcome.
Okay. I guess this is the time to end because we are running out of time. So again, thanks all of you. Okay. Thank you, Markus.
Okay, my pleasure.
Okay. Okay.
Have a nice evening, and we'll hope to see you soon.
Goodbye, Markus. Goodbye, Jean-Pierre. Okay.
Bye-bye.
Bye-bye.
Goodbye.